So the idea, what I'm going to talk about is, in heavy quark physics or various physics related to heavy quarks, lattice results play a quite important role these days. Rishi today referred to some lattice results, and I wanted to discuss a little bit how those results are obtained. Well, in particular, I wanted to spend most of my time on how kind of a close cousin of the heavy quark effective theory, or in fact, heavy quark effective theory, but at rest, is put on lattice. Okay, so you already had a lattice talk, so I presume you know some basics about lattice, but let me anyway mention a little bit what is done when people do some QCD calculation on lattice. Let's say a mass calculation. So the name lattice comes from the fact that you essentially imagine that the space-time is not continuous. It's like a lattice, and that is essentially the requirement is that in quantum field theory you need to put a cutoff, and that cutoff manifests as lattice. So let's say you say that all my fields reside not on arbitrary points, but on these points. Okay. So then, as you know, so let's say if you take the boson action, for example, so that's phi del 2 I. So I am doing this in Euclidean space, so time has been rotated to IT. And this in continuum gives you, when you go to momentum space, you get half pi k. Like that. Now, if you put stuff only on this lattice, then these derivatives, of course, will get replaced by finite differences, and you also know what's the discretization of del 2 phi. So this will become sorry. So now I have finite number of points. Square, and then there will be sorry. Right, and now if you do Fourier transform, so replace pi n by integral k to I k dot n. So should be NA. A is my lattice spacing. Okay. Okay. And as you know, if there is a lattice with lattice spacing A, then there's a momentum space cutoff that we get. All the momenta are restricted minus pi over A to pi over A. Okay. And if you replace this over here, then you will get that this term gives you, instead of that form of integral A over this range. Okay. Yeah, that's right. Okay, and this, of course, you can write as 2 into 1 minus cos Ka. Okay, this by A square. Now, of course, the idea is that the A or 1 over A puts a cutoff in the theory. So for the momenta that you are interested in, K should be very, very small. K should be much smaller than 1 over A, the cutoff scale. And that will give you back this half K square plus M square when you expand the cos of K. Of course. Thanks. Right. Okay. Fermions. The continuum action for fermions, of course, is so again, I am gone to Euclidean space. Okay. And so this, oh, okay. Let me start with gamma mu del mu, and then I will change the del mu to d mu when I introduce gauge fields. Okay. And again, you know how to discretize del mu psi of x. So this will give you psi bar x, gamma mu. It turns out, for some reasons that many of you may be familiar with, is that it's not a good idea to start with only this much, this Lagrangian. So you are, okay, of course, I can add extra terms to this Lagrangian. See, this Lagrangian is supposed to give me the continuum Lagrangian only in the limit A going to 0. Clearly, this is not this, but in the limit A going to 0, this will go to this. Similarly, I can add other extra terms, and it turns out that we actually, for this theory to make sense, I need to add another term which is proportional to A, the lattice spacing. Okay. And essentially, the reason is that if you just try to work with this part of the Lagrangian, then you end up getting, rather than one species of fermion, you end up getting lots of species of fermion. Okay, and so now you also know how to, we have already discretized that. So if you put all of that together, you will get something like a Lagrangian, which will go like summation n mu are the directions, 4 space-time directions. N it should be obvious what is coming from where, right? So this plus this minus this gives you the double derivative. And then this and this gives you the gamma mu del mu. And of course, this is the mass term. Okay. So let us look at the static Lagrangian. So what if I want to work with the kind of theory that Abhishek was talking about? So I'm interested in the time derivative term in here. So the special momenta are much smaller, and I'm only interested in the mass is much larger than the typical special momentum. And so my leading order Lagrangian will only be the special derivative term. Okay. So then the Lagrangian will, sorry, I did not say what to do if you want to introduce gauge fields, but you already know that the job of gauge fields is so when I have a derivative, I want to do arbitrary rotation here and here, then the derivative term does not have a nice transformation, and I change the derivative, introduce a gauge field in there so that that thing has a nice transformation property, right? So here, when you look at this expression, it should be clear how I introduce gauge fields here. So psi bar n under a gauge transformation will go to V of n psi of n. Psi n plus a mu, of course, will go to V n a plus a mu. So if I want a term like this to have a nice transformation property, I will need to introduce a gauge field here. So U that connects n plus a mu. Okay. And the transformation property of U will be under gauge transformation, it will go to so wherever there is a term like this, so when you look at that transformation and you look at this term, should be able to figure out that what I need here is a U dagger n minus a mu n. Okay. And then of course there will be, so these are the covariant equivalent of the covariant derivatives, and there will be the equivalent of f mu nu square, which I will write in terms of these U's. Okay. So let us look at what happens to, what is the form of this term, the zeroth component, the time component of this term, that is psi bar n 1 minus gamma 0 u in n plus a in the time direction. Okay. Now, if you remember Vishek's lectures, can you figure out only one of these terms is giving me the kinetic term for Quark, and the other one is giving kinetic term for the anti-Quark. Which one is doing what? Which one is the term for the Quark and which one is the term for the anti-Quark? U dagger. So this is U that goes from n to n plus a t hat. Yeah, I'll sometimes use 0 hat or something. So time direction. Remember the projection to the quark fields were with 1 plus gamma 0. The projection to the anti-quark fields were with 1 minus gamma 0. So clearly the term with 1 minus gamma 0 here will give the anti-quark kinetic term, and this is the quark kinetic term. Okay? And so you see, the quark kinetic term is only connecting n to n a minus at. So that's like a kind of a backward derivative kind of term. Whereas the anti-quark term here is a forward derivative term. Okay? Right. So you can, of course, quite easily figure out from these what will be the form of the and of course there were. Well, I took this whole thing, and okay, so only this team. I dropped this team, but let me add that -2. Okay. No, so for this object, I just wrote the 0th component.
So you explicitly write it.
Yeah, I wrote the whole thing. There's no tricks here, and I then claim that this is the kinetic term for the anti-quark, and this is the kinetic term for the quark. Okay, and so the quark term has a backward derivative term. So, and you see that, of course, as will happen with the backward derivative term, that there will be an U dagger that connects. So when I'm looking at the kinetic term for the point n, then that connects to n minus a. So let's say this is time direction. Okay, that connects to n minus at. Okay, and the corresponding gauge field that comes here is an U dagger. Okay, so that's like a backward going stuff. And so from these, you can probably intuit, or you can work out from this. It's not difficult, but should be obvious that the quark propagator okay, this is quark, so of course it's forward propagation. And so once I say that the only thing that connects quark fields at different space points are the special derivative terms. So if I say special derivative terms are not in my leading order, then of course you just have the time slice. So therefore a delta x minus y. Okay, the static quark does not fluctuate in time. Okay, and now I will have this gauge link. It will be like a And of course, there will be this projector which projects to 1 plus gamma 0. Okay. So, okay, maybe I should have said why I am doing all this. So let us say the motivation is something like what Rishi was saying in the morning. I want to calculate FB from the lattice. Okay. What is FB? Well, if you have a B quark, not B quark, sorry, a B meson, a pseudoscalar B. Okay, let's say zero momentum. And so the decay of the B meson is essentially, so you put an A0, that takes you to vacuum, and this object will be square root of FB type. That was the notation we used, right? Yeah. So how does one calculate such a thing on the lattice? So that's right. Yeah.
So maybe you can put a P0.
P0, that's right. Yeah. Of course, because it's a vector, so I need that. Right. So how does one calculate? And P0, of course, when I have P is equal to 0, then that will just give the mass of the quark. Mass of the meson. Gamma 5. Q bar gamma 0, gamma 5 Q. Yes, right. So how would I calculate this thing on the lattice? So I wrote down the Lagrangian. I did not say what we do with the Lagrangian. So the whole point in going, so you know that in quantum field theory, when we calculate something, so any observable O that let's say have the Fermion fields and the gauge fields, okay, we calculate that by calculating a partition function like I have again written it in Euclidean space. In Minkowski space, this will be I times S, right? And Z is just this thing without this O. Of course, we know how to do perturbation theory with this. But where perturbation theory does not work, we can, for example, use the lattice discretization. And then, so these are all these functional integrals, of course. Okay. And when I have lattice discretization, these psi bar psi, etc., are not continuous functions of space-time. They are like discrete variables. And then this from the functional integral, it becomes a normal integral over, however, a very large number of yeah, here I have written a mu, but usually what we do is use those kind of u mu's, which are like exponentiating this a over this. It doesn't matter. I'll mostly talk about what happens to the Fermion fields. Okay. Further, so the point is that, okay, so I have transferred a functional integral into a multi-variable integral. What have I gained? The point is that once I have this in this form, I can try to do a Monte Carlo integration of the whole thing. Okay. Now, Monte Carlo integration, of course, requires me to give some values to these fields U and try to find what are the probable values. I cannot do that with psi bars and psis because these are Grassmann numbers. So what one does is, on the other hand, these psi bars and psis appear only as quadratic pieces, and you know how one can integrate them out. Okay, so whenever there is something in a quadratic piece, you can integrate that out, and that just gives a inverse of this quadratic term. So if this I call A, and integrating out psi by psi. So what I mean is this. So if I have something like let's say for this O psi by psi, psi x, psi bar y, and then this e raised to minus summation psi bar n a n m psi y, then the result of this integration will be A inverse xy. Okay. And this is also, of course, this is what we normally call this propagator, that gxy that I have written over there. Okay. Now, what I do when I want to do this calculation is essentially start from the vacuum field configuration. Okay. Create a B field. Okay. So let's say at some point in time, I want to create a B field. For that, I give some operator which has the correct quantum number as B. So let us put in B bar gamma 5. So if it's B plus, then it will be if it's B plus, then it will be U bar gamma 5B, right? Yeah, U bar gamma 5B. Yeah. And then there will be the A0 field, which destroys that UB bar field. So this, of course, creates a UB bar from the vacuum, right? And I want to destroy that, then I will put in a B bar. So I create this at some time, let's say t is equal to 0. And then at some later time, B bar gamma 0 gamma 5 at some later time t. I put in this field. Okay. So essentially what I need to calculate is something like such an expectation value where my O is now this field. So what does this actually give me? This gives me that a field like this was created from the vacuum. Okay. Then it propagated for some time from t is equal to 0 to some later time t, and then it got annihilated. Okay. Now, there is a Z factor for creating a wave function denormalization factor for creating the B from the vacuum using this operator. Okay, so the result for this will be whatever is the wave function factor for this Z of P. Then this B meson propagated from 0 to T, right? So propagation from 0 to 2 in Euclidean time will give me an e raised to minus E of the quark, but if I am doing at 0 momentum, then it will be e raised to minus mb times E. And then this object gets annihilated by this object to go to vacuum. So that will produce another wave function. Okay. So this will be the leading order result, especially if you go to very large T. There may be corrections, but let us say I want to calculate something like this. Okay, good. Yeah, so I did not write the explicit spacing there, but let us say I projected everything to special momentum 0. Yeah, the way it is done is that this point current, which is at some point x, now I integrate it over all space-time. Okay. Sorry? Yeah. This also do ZA? Okay. That depends on your notation, right? I mean, remember, this is not the, so this is the total function enumeration for this whole thing. So I can, yeah, give it some name. Okay. Of course, you will need to U bar gamma phi B. Yeah. See, here you could have used any operator that creates a B. So eventually you will try to cancel out this ZP factor. Okay. What you are interested in is this object, because this tells me how the B is destroyed by this point current. Okay. And that is what is connected to FB. Okay. So this, of course, is not a heavy quark propagator. So this can fluctuate in space. Okay. And this object will be in the static limit. This will be like a line. Okay. Yeah. Right. So, okay. So as Abhishek, so in the full theory, if I want to calculate this object, then essentially what that will give me is one propagator for this, another propagator for this, and of course these extra gamma factors. And I have to average this over this whole thing. So I will do a calculation like this, O psi bar psi A, where my O is essentially a B quark propagator E is equal to 0 to T, then gamma 0, gamma 5, and then an U quark propagator. So let me write GB, and then GU from E to E is equal to 0, gamma 5. Okay, just what's called weak contraction of this expression. This is in large scale limit, yes. Yeah. Okay, so right, so modulo some complications. I'm just trying to outline. Yeah, so the gap between the lightest mass and the excited mass, yes, right. Okay, so so I can calculate this. Of course, I calculate this on a lattice A. What are the conditions on the lattice spacing A? That it has to be much smaller than all the scales in the theory, including MB. Okay, including the mass of the B quark. And of course, that's not enough, because I do not want to give you the result. I mean, as you know, when you do any quantum field theory calculation, you put in some regulator, you do your renormalization, and then you get rid of the regulator. So eventually, I will need to get rid of the A also. Okay, so small a few values, and then eventually I will get rid of A after the lattice spacing A. Okay, after doing some assessing. What else do I know? That the lattice should be sufficiently large also, so that the B meson, which is an object of a size, let's say a Fermi, okay, doesn't feel like cramped there. Because of course, what I want is an infinite volume result. Okay, and it turns out that how large a lattice I need actually depends on the mass of the pions. Okay, so let us say I need something like a 4 Fermi lattice. Okay, because the pion mass is a little less than, little more than 1 Fermi inverse. So something that is substantially larger than that, let us say 4 Fermi. Okay, and MB, of course, is let's say about 4 GeV. Okay, so 4 GeV inverse is about 0.05 Fermi, right? And then if I want, okay, so I want something which is substantially larger than these and a few values of them, okay, so that I can then eventually take A going to 0, okay? And the lattice size should be at least 4 Fermi. So you can see that this will need a pretty large lattice, okay? So that is why directly doing these calculations on lattice, where you just put the B like that is difficult, and that is why we go to this effective theory. Okay. And so what will one do in this effective theory? Well, the major requirement that the lattice spacing has to be this small will be gone. Because now, once you have gotten rid of exactly the way Abhishek and Rishi were doing, in these all kinds of heavy quark effective theories, you take the heavy quark mass completely out of the equation, saying that's not an important scale, that will just give some additive correction to stuff. Okay. And then essentially the next important scale for the B meson becomes something like lambda QCD, okay, which is few hundred MeV and not 4 GeV. Okay. And then, of course, you know how to do the calculations of the lattice. So that is the whole purpose, of course. So what we will do is do the calculation exactly as I have outlined there, except the B meson will not come as a B meson. Its propagator will be replaced by that static propagator. Okay. And the U quark will remain as it is. Okay. The advantage is that now we do not need a lattice of 0.02 Fermi, etc. If I want, yeah, I can take a 0.2 Fermi lattice. Well, that's probably a bit coarse, but whatever. So 0.1 Fermi lattice. So that looks like a factor of 2, doesn't look much, right? But you remember this is 2 to the power 4. It's a 4-dimensional thing. Okay. So that's quite a bit. Okay, and this 0.05 Fermi, I said, was the coarsest lattice I can have. Actually, if I want to put physically a big quark on the lattice, I will need substantially smaller lattice spacing. Okay, so yeah, you can write, so it's only the 1 plus gamma 0 component which will be important. So it will be much smaller. The spin will essentially not play any role in the leading order stuff. But then, there will be all these, I mean, of course, you will not just take the static thing, right? I mean, nobody does a real calculation with only the static Lagrangian. Okay. So let me first say the main idea of what one, I mean, I guess the main idea of why one would like to put an EFT, I mean, lattice, we always say it's a first principle calculation. We start from QCD, we do a calculation. Instead of that, why am I trying to put an EFT on the lattice? I hope that came out, and the broad outline of the program, how I do it, also came out. But of course, I mean, as you know, it's all the complications start after this, and in particular, the matching that Rishi was talking about today, that's the most crucial part. I mean, you need to match those static currents to the full QCD current, right? But even before that, I mean, so yes, good question. That's what I was actually coming to next. Yeah. Yeah. Of course, the total Lagrangian is, so let me write now in a bit more, let's say continuum-like way. Okay, so what I said was that in the leading order, I am only concerned about the psi bar D0 psi, or let me write it as, so L in the leading order, I will write LH static plus LH bar static, where LH static is psi bar is D0 psi H. And okay, you could keep the M plus D0, but then normally this M term is just an additive constant in everything, so that you can just drop and then later just add to give the B meson its correct mass. It doesn't play any role in the dynamics. And similarly, LH bar static. Okay, and of course, E plus H psi H. And for H bar, this will be corresponding P minus, where P plus or minus or 1 plus or minus gamma 0. Okay. And then will be all my 1 over m correction terms. Okay, so for example, everything that has got to do with the special derivatives, etc., will be correction terms, and you probably know the forms of many of these 1 over m corrections, but let me write them as, so 1 over 2m LH, what should I say, order 1, let's say, because it's 1 over 2m. And then there will be order 1 over m squared terms. And these terms will have terms like, so that's d square and then 1 over 2m, so that's your standard kinetic term. And that's the spin-spin interaction term. These are the two 1 over m terms. Of course, this is what you get if you just do like a classical field theory. I mean, the way Sakurai goes from Dirac equation to the non-relativistic Lagrangian. Okay, when you are treating it like an effective field theory, you know that the coefficients will be arbitrary at this stage, and you will do a matching of those coefficients, right? And similarly, it's very easy to, so if you do, so you remember how the non-relativistic Lagrangian is obtained, right? You do some Foldy transformation with e raised to gamma dot d, something like that, by m or 2m or something, by 2m, I guess. No, I'm just saying the Foldy transformation. It's not important. I just wanted to say in that exactly the same language, what will be the leading correction to the A0 term. So when you look at this correction, then you know that the A0 will go to, again, let's say u bar gamma 0, gamma 5, h of x, and then plus 1 over 2m, u bar gamma 0, gamma 5, gamma dot d. Okay, so is that my 45 minutes? Okay. Okay, so shall I take 10 more minutes? 5 more minutes?
You're swimming.
Okay. Pritam, how much longer can I go on? Okay, so what I, okay. So when I write it like this, the total calculation, of course, becomes so O leading order, which in this case is the static part of the A0 current, plus let's say 1 over m O1, okay, e raised to minus integral. So L leading order, where L leading order is that LH plus LH bar plus 1 over m L1, and of course there are higher order terms. Now, to answer Abhishek's question, see the LH and LH bar they just have dimension 4 terms, right? Because this was just psi bar D0 psi. So in normal dimension counting argument, you would expect a Lagrangian where I'm doing the work only with L0, L static over here should be renormalizable, okay? And it turns out people have, I don't think, okay, so to my knowledge, which is based on reading review articles, the renormalizability has been checked to 3-loop level, but not to all loops. So there is not an, but naively you would expect from our standard intuition of dimension counting that it should be renormalizable. And then there is indirect proof in the sense that you can actually do the calculation on lattice using the static Lagrangian. And then you see whether you can just take the going to 0 limit. It works very well, okay? Yeah. Tuhin asked me to give a Blackboard talk, otherwise I could have shown you some of the results. Later, after I came here, Tuhin said, oh, he was not that serious about it, but I'm very scared of him, so didn't take it. But I'll give you a reference where there are various plots which show how you can take the going to 0 limit numerically, okay? And so we have reasonable confidence that with the static Lagrangian, you can take the continuum limit, no issues. Okay. Of course, just by pure dimension counting, you know that once you allow L1 in here, things will not be renormalizable anymore. Yeah, so there are two, so essentially you can, first the lattice spacing effect itself is very small. Then you can start with different discretizations, and they all come to the same point as you would expect a normal continuum limit. Okay. Yes, so okay. I will probably spend all my time in static, but those are some of the other things you can do. Yeah, so definitely you can take other discretizations. In this case, I am saying that I am only keeping the L0 in the operational part of the renormalization. What I will do is expand this part and bring it down here to here, okay? So a pure static calculation would essentially treat this as minus 1 over m L1 and plus 1 over square. Okay, so this will be a pure static calculation, and then things are renormalizable. Every term that you take, you can take the continuum limit and all that. So, and the final, okay. And then the remaining part is the matching. Unfortunately, it's the most complicated part of the whole calculation. So people who do the FB using this static limit, so this alpha collaboration, okay, and it's based in Germany, and you could have guessed that it's Germans. So very rigorous and painstaking calculation for this matching. Okay, so I'll give you a reference if you want to look at the details. This is a review. Okay, and now I will very broadly say what's the plan, how they do it. I mean, of course, you can do it perturbatively. Okay, perturbatively matching the static current to the full QCD current. So what you want essentially is to calculate a number of observables in the static theory and in full QCD, okay? And then tune the parameters of the static theory so that, so let us say you calculate some observable phi in QCD, okay? It should agree with phi in, let's call it heavy quark effective theory, okay? So in this case, what I'm doing is more like static theory, okay? Now, of course, when you look at this, you immediately say, oh, well, excuse me, didn't you say you cannot do the calculation in full QCD? So how are you going to do this matching? I mean, of course, you can do it perturbatively, but then it doesn't remain a fully non-perturbative calculation, and it actually turns out that these matching coefficients, they are pretty non-perturbative. Okay, when you look at the numbers people obtained. Okay, so you need some kind of a non-perturbative matching scheme. So what is done is this. Okay, first you do the matching without caring about. So I want to do the full QCD calculation. So clearly I need a small lattice spacing. So let us get rid of the requirement of the lattice being sufficiently large. Okay, let us do the matching at a lattice of, let's say, L is equal to 0.45, let's say. Okay. So you calculate a bunch of observables. Typically, if you want to do the calculation to order 1 over m, it turns out that I think you need, how many parameters do you need? I think there are some total 5 parameters that you need. One is to tune just the bare mass, and 2 parameters in this order 1 over m Lagrangian, and 2 parameters for matching the A0. Okay, so you need to calculate 5 observables. Okay, this tuning is first done at a lattice which is sufficiently. So let us say 0.4 Fermi, 0.05 Fermi. Okay, so now the next requirement. You do not want to do a matching, you do not want to match with a QCD at 0.05 Fermi. So you take the continuum limit in this side, you take more than one lattice spacing, you do the QCD calculation, however, at a finite volume. Okay, so the QCD, whatever matrix elements, phi's, are calculated at finite volume. Let's call it L1, which is sufficiently small, but I have taken A going to 0. Okay. Now I match it to a heavy quark effective theory at some finite A and the same L1. Okay, so I have these bunch of parameters for my static theory for the lattice spacing at which I am calculating. Okay, then with the same, so this is where what observables you take become a bit crucial, because you kind of want the scale in the theory to appear through this L that you are putting from the outside. But anyway, so the plan is that now this HQET at size L1 you match to another HQET, let us say. So not much larger, okay, one step up, okay. So that gives you some kind of a, what would be the equivalent of a beta function for this particular matching coefficients, okay. You go from a scale L1 to a scale L2, okay. So you are doing the lattice calculation, static calculation on some lattice spacing, no? So you want the parameters that you want to use for that static Lagrangian. So whatever is the A that you are using in that calculation, for that A. And then you will do that. Yeah, so it's a continuous process. You will, here you want to take a continuum limit of this. You want to take a continuum limit of this. But these are all HQET calculations. So they're simpler in some sense, okay? So you do this at more than one lattice spacing, you take the continuum limit. You do this at more than one lattice spacing, you take the continuum limit, and then you essentially have to do another step up. So if you need a factor of 10 here from 0.4 Fermi to 4 Fermi, let's say you do it in 3 steps, something like that, okay? And then once you have taken the continuum limit for each of these, then you essentially get a discrete version of the integration of the anomalous dimension, so to say. Okay, so the discrete version of the matching coefficient that you were talking about. So, yeah, I mean, we kind of knew that I will not be able to give the details of this, but it's pretty elaborate and you can, for example, that reference, that's a review article that explains in great detail the program. Okay. Let me now give a couple of examples of uses of this. So using this, of course, they have calculated FB. Okay. And there are other ways of calculating FB also, which are also don't, I mean, okay, so this is in some sense more rigorous in the sense that they are keeping track of the lattice cutoff at every space. The other thing that you can do is you try to, so I was part of a calculation of FB, for example, where we played with the, so we took the full Lagrangian and we played with the tuning parameters to get some cutoff effects small, okay, and then kind of did the calculation with that. And there are other methods that people use. So let us say FB that they get from this static program for two flavors. I'm just quoting one set of numbers. 186, 13 MeV. Okay. The result, for example, we had got was 197 plus 24 minus 17, okay, plus 11 minus 2. And the reason why we have all those extra error bars is because of this fact that the cutoff effects were not taken into account that well. So these are kind of systematic effects which kind of tried to make an estimate of how much error could come through that. Okay. But you can see that there's very good agreement. And in fact, the flag average of all theoretical calculations that, okay, this is not the latest one, I think, but the 2019 flag average was 189.8 MeV. So you can see this static result is in excellent agreement. There are other purposes for which you can use the same static Lagrangian. In fact, I was part of a calculation where we tried to look at how a heavy quark loses its momentum in a quark-gluon plasma. And as you can guess, I mean, this is almost like prepared for if you are looking at B quark, then it's very similar to why you should use this static Lagrangian. And again, you calculate this static line and how it interacts with the plasma. And kind of the state-of-the-art results there are from this static approximation also. Okay. Let me just say one more thing and then I will stop. This is, of course, all for HQET, for heavy light mesons, or the other example that I gave where an individual heavy quark is moving through the plasma. This does not work for quarkonia, for example. Why? This Rishi must have discussed. Sorry? Yeah, so the point is that there, the kinetic energy term, P square by 2m, so P, in this case, P does not depend on m in the heavy light meson case. Because, you know, if you are in the center of mass frame of the heavy light meson, then the heavy quark momentum is same as the light quark momentum. The light quark momentum is of order lambda QCD, so is the heavy quark momentum. But in the case of heavy light quark, quarkonia, this P square by 2m is of the order of the contribution that you get from the potential term. Okay, so p square by 2m. So p scales somewhat with m. And so p square by 2m is not 1 over m suppressed anymore. And so you need to do something else. Okay, so you need to do the full NRQCD. Okay, so I will not go into the NRQCD because Tuhin is standing. But essentially, the difference from these and NRQCD is that you will start with that same Lagrangian over here, okay? But then you are not allowed to do these 1 over 2m, etc. terms coming down. You have to at least include the kinetic energy term also in your evolution. And actually, Dev Shubhra is the expert in NRQCD. Tuhin may have talked about NRQCD on lattice, right? Sorry, not Tuhin. Nilmani when he gave his talk. So most of the calculations Nilmani presented, I would guess, were from an NRQCD based calculation. Works very well, but this one and many of the leading Quarkonia results are from NRQCD approximation. But there, what Abhishek said is valid. You cannot take the continuum limit precisely because of the fact that you now have these 1 over 2m LH, etc. terms in the Lagrangian, which are of higher dimension 4. Okay, so yeah, I guess I stop here.